Hi everyone, today we're going to be talking about properties of integrals. So for each property, I'm going to give you what the property is and hopefully try to illustrate it so we know where it's coming from. So on this page, there are 6 properties that we need to be familiar with. So the first one has to do with the order of integration. So what I notice here is I'm integrating from a to b of my function f of x, and they're telling me that's equal to s. So what I think of when I've got a picture, I know that the integral from a to b represents the area trapped between the curve and the x-axis over that interval. So the idea here is if I'm going from a to b, they're calling that area S. Now what happens is if I switch that order of integration, so instead of from a to b, I'm now going from b to a, I'm going backwards, so this is going to change now to negative s. So if I'm going backwards, that value that used to be positive, I'm going to take the opposite of it now because I've switched that order of integration. So that's property number 1. The second property is called the zero property. So this one says the integral from a to a of f of x dx. Now, if I just integrate from a to a, I haven't accumulated any area. So I'm going to make a note here that there is no area accumulated. So in that case, since my integral represents an area, the integral from a to a of f of x dx is just equal to 0. Okay, the next one is our constant multiple. So before I kind of talk about the rule itself, I want to illustrate what we're talking about here. So I'm going to start off, let's consider a function, I'm going to say f of x equals x. And I can go ahead and graph that. Okay, so let's consider the integral from 1 to 3 of f of x dx, so x dx. So I know the graph of f of x looks like this, or excuse me, of f of x equals x looks like this, so it's a line. And then if I were going from 1 to 3, I know that's from here to here, that area. And so there I have a trapezoid, so it's going to be the height is 2, so 2 over 2, base 1 is just 1, my base 2 here is 3, so my area is going to be 4. So if I just have a function x, so y equals x, the integral from 1 to 3 is just 4. Now, I'm going to consider, the idea here is that we're multiplying our function by a constant. So now let's consider the integral from 1 to 3 of x dx, but now I'm going to multiply by a constant k, and just to be a little more concrete, let's call this 2. So now instead of x dx, I have 2x dx. Our limits of integration haven't changed, I just multiplied by a constant. So now my function is 2x. So let's see, at 1, my y value is 2. At 3, my y value is going to be 6. So now my line looks something like this. And when I'm talking about the area, I've added on all this area as well. So the total area is all of this. So let's see what that is. So that's going to be now, I still have a trapezoid of height 2, so 2 over 2, but now my base 1, this right here is 2. My base 2 goes all the way up to 6, so now my area is 8. So what I noticed is when I multiplied my function by 2, I actually doubled the area as well. So what that tells us, and sorry, I'm going to do this up here, is when I have this integral, what I can do is just take the integral out, or the multiple, the constant multiple outside. So I'd have k times the integral from a to b of f of x dx. And since we knew that integral from a to b of f of x dx was s, that would just give us k times s. So the big idea here is if I have a constant times a function, I can just move the constant outside of the integral. All right. The sum and difference rules are pretty straightforward, so I'm not going to really draw those out. If I'm taking the integral of the sum of two functions, that's just going to be the sum of the two integrals. So I could write this, the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. Okay, now the addition rule, and I think you guys have already seen this in some of the practice we've done, but here's what it looks like. If I draw a curve and I have A and B and C, what we're representing here is first this integral, the area or the integral from A to B of f of x dx, we know would be represented by what's in blue here. And then I could look at my second integral. The integral from b to c would be this area here. So really adding those two areas together is going to be the same as the integral now from a all the way to c of f of x dx. And again, that's going to work provided that this upper bound matches this lower bound so that those areas are right adjacent next to one another. Excuse me. All right, the last one is probably the hardest to kind of visualize, and so I'm going to do my best to do a picture here, and then we'll also talk through it in class. So here's the idea. I'm going to start with an example. So again, I'm going to use my function f of x equals x. So let's look at the integral from 1 to 3 of x dx. So I'm going to draw that here. So let's see, when x is 1, my output is 1. When x is 3, my output is 3. So I have basically this area here in blue. Now, in this case, what we're doing is we're adding a constant to our function. This k is a constant. So let's do that here. Let's pick, instead of f of x, I'm going to do f of x, and we'll go back to our, let's see, we'll go to x plus 2. So in this case, that constant k, we're just calling that 2 here. So now let's find the integral here of 1 to 3 of x plus 2 dx. It's our same function here, f of x, but we have added a constant. And let's see what happens here. So I'm going to draw myself another set of axes. So now at 1, my new output is 3. At 2, we should go up to, or 3, excuse me, would be at 5. 1, 2, 3, 4, 5, up here. And so now what we're looking at is all the area trapped under here. But what I want us to realize is this area that was here is still represented right here. What we've done by adding that plus 2 is we've shifted this figure up 2, and in doing so we created this new rectangle. Right? This rectangle of area was created by that vertical shift, or the plus 2. So what we do when we add a constant is we add a rectangle under the area. So what we can really do here is I know this whole integral is going to be the same as the integral from a to b of just my regular function, right? That was the blue part. And then I added an area in the shape of a rectangle. Well, the base of that rectangle is just b minus a. 3 minus 1 gave me 2. In general, the base of that rectangle is b minus a. And the height of that rectangle was the value of k, the value of that shift. So b minus a times k. And again, this is that red rectangle where this is the base of that rectangle and k would be the height. And I know this is probably the trickiest one to kind of get around, so we'll talk about that in class if you have questions. So now the rest are just some problems going through and using these properties. So let's look on the next page. So we're going to use the rules for definite integrals and the following known values to answer these questions, to evaluate integrals whose value we don't know. So the first one asks for the integral from 4 to 1 of f of x dx. Now, I know using a property that if I switch that order, I have to take the opposite sign. So this is going to be the same as the opposite of the integral from 1 to 4 of f of x dx. I know that the integral from 1 to 4 of f of x dx, now this integral here is a known integral. I know that's equal to -2, so I'm going to have this is equal to the opposite of -2, and that just gives me a value of 2. So I applied a property first and then used these known values to answer that question. So for number 2, now I want the integral from -1 to 4 of f of x dx. So right away, I know this is not going to be helpful because that has to do with h. So I have two integrals for f. One is from -1 to 1, and one is 1 to 4. Well, using my addition rule, I know this integral is actually equal to the integral from -1 to 1 of f of x dx plus the integral from 1 to 4 of f of x dx. And again, that works because this upper bound matches this lower bound. And so now I can add those known values together. I have 5 plus a -2, which is going to give me 3. All right, let's see. I'm actually going to leave 3 and 4, and then we'll look at a couple more down below because these tend to repeat themselves. Let's see. Let's do numbers. What do I want to do? Let's do number 2. All right, number 2 down here is asking for the integral from 0 to 2 of g of x dx. So I know I'm only concerned with these two integrals. Now, I have the integral from 1 to 2 and the integral from 0 to 1. If I'm looking, oh, this isn't what I wanted to do, but we'll keep going. If I want the integral from 0 to 2, I'm going to add the integral from 0 to 1 of g of x dx plus the integral from 1 to 2 of g of x dx. Now using those values, I have 3 plus a -1, and that's going to give us 2. All right, next we'll do 4. All right, now 4 is an example of the rule we had where we are adding a constant, right? So what we know is this plus 5 took the area I would get when I integrate g of x and it shifts it up, creating a rectangle. So if I'm applying that rule, what I have here is this is going to be equal to the integral from 0 to 1 of g of x dx, and then shifting it up created a rectangle. The base of that rectangle was this length 1 minus 0 times that vertical shift up 5, which is the height. So now I can find the value from 0 to 1 of g of x dx is 3, plus I have 1 times 5 is 5, and we get a value of 8. All right, so we'll fill in the other examples just for practice when we're back in class. Now, one big thing that catches students all the time, there is one thing that you cannot do. And that thing that you cannot do is there is no multiplication rule. So from 0 to 2 of f of x times g of x is not equal to the integral from 0 to 2 of f of x dx times the integral from 0 to 2 of g of x dx. Again, I'm just going to put a whole big red through this thing. Students get caught on this over and over again. You cannot multiply like that. That is not a property of integrals. All right, that's enough for today. Thank you for your attention, and I will see you back in class.